Okay, then I'm going to go back to the Monge-Ampere equation. Okay, so we've seen the PDE come up in optimal transportation. We've seen a couple different notions of weak solution of it, but I cheated or oversimplified, or however you want to call it, at the beginning and said, let's pretend we're just doing the Dirichlet problem. Of course, the Dirichlet problem does not necessarily make sense if we're actually trying to solve optimal transport. So what boundary conditions do we really need? This pen is on its way out, I think. All right. So boundary conditions for the Monge-Ampere equation. Okay, so what do we have? We have a domain, and we have some kind of target, whatever it is. All right, we're solving a Monge-Ampere equation, which involves the densities on these two sets. And what do we want at the end of the day? At the end of the day, we expect our optimal map to be given by the gradient of u. So another way of writing this, I guess, is that for all x in the domain, I want the gradient of u to be contained in y, or y bar. Right? Nothing's allowed to escape. All right, so this gives us what's called the second boundary value problem, okay, for the Monge-Ampere equation. Okay, so we've got our PDE. Okay, we had this extra constraint. And now our boundary condition becomes exactly this condition, that we don't want mass to escape. So gradient of u of the domain, that's a capital X, is contained in y bar. So this doesn't look like a boundary condition that you've probably seen before. In fact, it doesn't actually really look like a boundary condition at all, right? A boundary condition, says at each point x on the boundary, I have some equation that it should solve. And this is actually a global constraint on the gradient of my solution. So that's a little bit different. We'll talk in a little bit about, can we make it look more like a boundary condition? But first of all, let's talk about if this makes sense from kind of a mathematical well-posedness point of view. So first of all, are solutions of this thing unique? No, why not? I can always shift by a constant. So as it stands, I don't have unique solutions here, right? And the reason I don't is because u of x itself never shows up anywhere in the equation. The only thing that shows up are derivatives of u, right? And that means if u is a solution, u plus any constant is also a solution. Right? So I don't have uniqueness as it stands. I have, at best, uniqueness up to additive constants. So right now, if u of x is a solution, so is u of x plus c. Okay, so we should have an extra constraint. That shouldn't worry you too much, right? Because at the end of the day, we actually don't care about u. We care about the gradient of u. So whatever constant we add in is going to fall out again when we compute our transport map. So that's no big deal. That shouldn't worry you, but of course you need to be aware of this. Okay, so we can add an extra constraint. Okay, so such as, say we decide that we want the average of u to be 0. We just take whatever we got, shift it up or down until it has an average of 0. Or we can decide that we want its value to be 0 at a particular point, or that we want its value to be pi over 4 at a particular point, or whatever. It doesn't matter. All right, what about existence? Is this guaranteed? I'm going to give you a simpler example, first of all, that you probably have seen before, and ask you if existence is guaranteed there. So, okay, I have some kind of elliptic PDE. What's the simplest elliptic PDE I can think of? Maybe a Poisson equation. And I have some kind of boundary condition, whatever you want to call this, that involves the gradient of u. So the closest thing I can think of to that that's easy is like a Neumann condition. It involves gradients. So say the normal derivative is equal to g on the boundary. OK, this has the same issue with, you can add constants to the solutions. But what about existence? Does this equation have a solution? Under certain conditions, right. So not if I just give you any f or any g, right? There's a solvability condition that has to be satisfied here. What's that? So it's really just doing like integration by parts. So we don't have to be too sophisticated here. What do we know? We know that if we integrate here, right, this is the same as integrating the Laplacian. Right? And if we integrate the Laplacian, what's going to happen? It becomes, what's that? So if I integrate the Laplacian, right, and I do integration by parts, right, I get something that really just cares about the boundary, right? And I get this du by dn showing up here on the boundary. Right, and this we know is equal to j. Right, so this is a necessary condition to have a solution. Okay, so the data, in other words, has to satisfy a solvability condition. Okay, so even in simple problems, linear problems, right, you can't just throw down any data that you want and say there's a solution. So there's no reason to expect life will get easier when we go nonlinear. But again, we can work this out. So back to our Monge-Ampere equation. Okay, and here our solvability condition really comes down to mass balance. So we're not creating or destroying anything. So what do we want? We want that if we integrate this, right, it should be the same as integrating g of grad u determinant of the Hessian. Okay, and if we do our change of variables, and we've seen this before, so let's let y equal the gradient of u, and we're integrating g. And what do we want here? We want this to get mapped onto our set Y. Right? We take this, we go through the gradient, and we want to end up with this target set at the end of the day. That's what our boundary condition is telling us. So this should be equal to g of y dy. Okay, so here again we have a natural solvability condition, and it's mass balance. So that makes sense. It makes sense really just from the physics of the problem, that we're trying to not create or destroy anything. So here the condition is mass balance. Okay, so those are just things to keep in mind. We need mass to balance, which hopefully if we're doing optimal transport, it does. And we need an extra constraint to actually pick out a unique solution, certainly. But what about this weird boundary condition? Can we make it look more like a sort of local condition on the boundary? So can we make the boundary condition look local? Okay, so maybe we'll take a couple iterations, but I'm going to start by saying, let's introduce a defining function for this target set. So this is a function that's going to signal to us whether we're inside the set, or whether we're outside the set, or whether we're on the boundary of the set. All right, so I'm going to call this h. Let's introduce a defining function. Okay, for our target. So this is what I want out of my defining function. I want h to be less than 0 if we're living inside the set. I want it to be equal to 0 if I'm on the boundary. And I want it to be positive if we're outside. By the way, do you know of any functions that do this? I don't know if you've seen this or not before. Jake, what function does this? A sign distance function will do this, yeah. So there's many ways of constructing functions that do this, but you can always build a sign distance function. And in particular, there's fast numerical methods for constructing sign distance functions. So for example, a sign distance. Okay, all that does is take the distance to the boundary of y and make it negative if we're inside, and make it positive if we're outside. And obviously, if we're living on the boundary, then the distance is 0, maybe to the boundary of y. Okay, so what do I expect? Let me draw this picture again. So I pick a point x. All right, see where it maps to. And it's supposed to land inside of my target somewhere. Okay, so if x is in my domain, then what happens if I plug this into my defining function? It's less than or equal to 0, right? So this point is supposed to land inside the target, and if it's inside the target, the defining function is negative. So this should be less than or equal to 0. So this is another way of expressing this sort of second boundary condition. It has the advantage this is local, right? Instead of saying the solution gradient everywhere has this property that says, now for every x, I have an equation or an inequality it has to satisfy. It has the disadvantage of being still not a boundary condition, right? It's still something that we have to impose everywhere. So this is local, but not on the boundary. Okay, so let's try to make it look like a boundary condition. Okay, so again, I have my domain, and it's going to some target. I want a boundary condition, so what I should probably do is ask what actually happens if I start out on the boundary here, because the boundary is really where I really want to impose some extra condition. So let's start on the boundary here. What would you guess would happen? You think it'll map to the boundary. That would be nice, right? It would be nice if it would map to the boundary. There's some, okay, if I just wave my hands a little bit, there's some reason to expect that's reasonable. We know that we have a map that has these nice monotonicity properties, right? So in other words, I don't expect a point that's over here to try to get twisted around and mapped over here. In some sense, it should pick up and hopefully land on the boundary. That's not a rigorous argument, but there's some reason to expect this might be a reasonable thing to do. So let's, with a question mark, say, does this land on the boundary? So let's let x be on start on the boundary. Can we assume that the gradient of u lands on the boundary of y? If I can, then this is nice. If we can, then again, I plug this into my defining function, and what happens? It's 0, exactly. So say this point lands on the boundary. If this is on the boundary, the defining function is 0. And we could write a condition like this. This looks promising, right? This is now, it's fully local, and it's posed on the boundary. This you could think of as like a nonlinear Neumann condition. So instead of just having a linear function of the gradient, which you'd have in a traditional Neumann condition, this has some kind of nonlinear function of the gradient. Okay, so if we can do this, we get some kind of nonlinear Neumann problem for the Monge-Ampere equation.
Is it supposed to be true for every defining function, or just that particular one?
Is it supposed to be true for every defining function, or just this particular one? So yeah, it would hopefully be true for every reasonable, whatever reasonable means, defining function, because all this is really saying is, does this point land on the boundary or not, right? And it doesn't really matter how H behaves as long as it satisfies these properties, right? If it lands on the boundary, it's 0. Otherwise, it's not 0. Typically, what you'll want is a convex defining function, which the sign distance function is if you've got a convex target. Okay, so then we get a nonlinear Neumann problem. Okay. Determinant of the Hessian times, I think I put the gradient, the g here, equals f. Okay, u is convex. And now instead of that funny global condition on the solution gradient, I have a local boundary condition. Nonlinear, but local. Okay, so this is now a local formulation, except for this extra constraint here. And actually, in your next homework problem, you're going to get to see how you can take this constraint and also turn it into a local condition. But this now feels like we can use some of the things we know about PDEs to study this problem. And it feels like we can use some of the things we know about numerical methods to try to actually solve this problem. The question is, does this work? Is this reasonable? I made a big assumption here that this gradient landing on here is good enough. So maybe this is my question. If I solve this problem, does the thing I end up with actually solve my original problem? Or am I going to end up with a u that allows gradients to wander, right, which we don't want? So this is the big question. If I solve this new problem, am I guaranteed to solve my original problem? Or in other words, I'm guaranteed to solve this part of my original problem and this part of my original problem. It's the boundary condition that matters. Am I guaranteed that gradient of u always lands in my target set? Right? If the solution of this problem has this property, then we've solved our original problem. So my claim is that we can do this as long as these sets are convex. So this is what I claim. This works if we have convex sets. Okay, so let me try to outline why this is reasonable. Okay, so I'm going to start with a convex function u such that, okay, at the boundary at least, at the boundary we satisfy this condition. In other words, for x on the boundary, the gradient of u lives on the boundary. So such that the gradient of u of x lives on the boundary of y for all x on the boundary of big X. And I want to show that actually the gradient of u always lands inside my target set. By the way, I'm going to do this assuming that I have a gradient here of u, but you can actually make this argument for the subgradient as well. It doesn't require really much additional work. I'll stick with gradient just to keep things a little cleaner here. So what I'm going to do is this. I have this function u. I'm going to build some kind of cone that lives below this. I'll call this cone V. All right, so let me explain to you where this cone comes from. So let's build a cone below u. What I'm going to do is run around the boundary of U and draw supporting hyperplanes around the boundary, and then just take the maximum of those supporting hyperplanes. Okay, so in other words, for each point on the boundary, I'm going to define a plane. Okay, call it Vz of x, which is going to be u of z plus gradient of u dotted with x minus z. Okay, this is just a supporting hyperplane to u at this particular point. All right, if I happened to be in 1D, what would happen? At this boundary point, I would draw this line, and at this boundary point, I would draw this line. Obviously, in higher dimensions, there's a lot more hyperplanes. And now I'm going to take the maximum of all of these. So the maximum is going to be this cone here. So I'm going to define v of x to be, it doesn't even have to be the supremum, it can be the maximum of all of these hyperplanes. So what are some things we can observe? V sits below u, yes? Right, because all of these things are hyperplanes, supporting hyperplanes, and supporting hyperplanes always sit below u everywhere. So when I take the maximum of them, we're still below u. So we certainly know that v is always below u. What else do we know? We know that v is convex. So I've taken the maximum of a bunch of affine functions. That's going to be a convex function. And each of these individual hyperplanes, right, has a constant gradient. It's an affine function. And its gradient is going to be given by the gradient of u at some particular boundary point. So gradient of Vz at any point is going to be equal to the gradient of u at this one particular point. All right, so what can we do with this? We want to try to use information about the subgradient of v. Okay, v is a cone now, it's not differentiable. But we're going to try to make some arguments about what subgradient values v is allowed to take on, and then relate it to the subgradient values of u itself, or the gradient values of u itself. Okay, so let's try to characterize the subgradient of v. We're going to do this via Danskin's theorem. Okay, to characterize the subgradient of v, so this is the hand-waving version first of Danskin's theorem, and then I'll write it down more precisely. V is given by the maximum of all of these hyperplanes. So say I'm at this point, and I want to know what is the gradient of v at this point. Well, first of all, I say, okay, v is the maximum of hyperplanes. Which hyperplane actually achieves the max here? I pick that hyperplane, and then I say, well, now this hyperplane has a gradient. The gradient of this hyperplane is the same as the gradient of v at this point. Right? So this is the idea. We say, I want the gradient of this. find the z that maximizes this, take the gradient of vz. That's what's going to do it. Okay, so let's do this more precisely. Let, okay, I'll do a script z be the set of maximizers. The reason I have a set here is because we can have points, right, that coincide with multiple hyperplanes. So this is going to be the set of all z such that v of x is equal to the corresponding hyperplane. Okay, so I said hand waving away, the gradient of v should be equal to the gradient of vz. But now there might be multiple vz's that I have to look at, right? Multiple possible slopes, right? So if I was down here, I'd have the slope -1 and the slope 1, perhaps. Now Danskin's theorem is going to tell me that the subgradient of this takes on all of the values between the slope here and the slope here. Everything between -1 and 1. And more precisely, something that actually makes sense in higher dimensions, it's going to be given by the convex hull of these values. So I look at the gradients of all my hyperplanes. I take the convex hull of that set. That tells me my subgradient. Okay, so dv of x is going to be equal to the convex hull. I'm going to write that this way, of all gradient values such that these guys are maximizers. Okay, so where multiple hyperplanes meet, multiple different slopes or multiple different gradients meet, this guy's going to try to take on those gradients and all the gradients, all the slopes that live in between them. Right? Again, which is just what we've seen in higher dimensions too. When we did this cone, we computed the subgradient of the cone, right? And we said, okay, except at the origin, the subgradient values lived on this unit circle, right? And at the origin, the subgradient was the entire ball. In other words, the convex hull of this unit circle. Okay, so we're looking at the convex hull of all of these values. Now, all of those values are equal to gradient of u values at the boundary. So this is certainly contained in the convex hull of all of my gradient of u values. All my gradient of u values at the boundary lived on the boundary of my target. We made that assumption, right? That's what we want our boundary condition to enforce. That at the boundary, gradient of u maps to boundary. So this is certainly contained in the convex hull of the boundary of y. And how can I write the convex hull of the boundary of y? What's another name for that? Not quite h. So here, okay, here's my boundary of y, all of these points. Now, what points are included in the convex hull of the boundary? The closure of y, exactly, right? So if I take all of these points, the convex hull says, pick any of them and draw a line between them, and that line has to be included in the convex hull, right? And I pick two more of them and I draw a line, and that line has to be included in the convex hull. And now we can reach everything inside of the interior of here. And that works. Okay, by definition, that works as long as this was a convex set to start with. So this is exactly y closure since I assumed that y is convex. Okay, so this cone we have a handle on. Okay, at any particular point, I don't know exactly what its subgradient is going to look like, but I know that its subgradient values, if I was taking this to be the thing that was computing my mapping, it would always land, its gradient or subgradient values would always land in my target set. Now what I want to do is use that fact to say, what about the gradient values of my original function u that I care about? Do they also have to land in the target set? Okay, and this is a nice result. We'll sketch out that these two things are touching at the boundary, right? You agree with that? Okay, they're touching at the boundary. V is always below u. And what that's going to mean is that if I look at the gradient values all around this set u, they're contained in the subgradient values of this set V. So this is my claim. Since V is less than or equal to U with equality on the boundary, okay, I claim that the subgradient, actually we'll just do gradient here, but subgradient also works. Subgradient of values of U over the entire set are going to be contained in the subgradient values of V over the entire set. Okay, so let's try to argue it. Let's let x naught be any point in the domain. And let p be equal to the gradient at this point. Okay, so here's where I'm going to try to argue that if I take any of these gradient values, they have to land inside my target set. So I'm going to define a number. This is going to be the maximum of, okay, I'm going to write this plane and subtract off my cone. And this is legitimately a maximum, right? Here I have some continuous functions that I'm taking the maximum of, and I'm maximizing over a compact set. So this max is legitimately attained. I can write this as u of x naught plus p dot x1 minus x naught minus v of x1, okay, for some x1. Geometrically, what would A be, let's say? So this is somehow a difference between a hyperplane, I guess, a supporting hyperplane, and V itself. And what are we trying to do? We're trying to find the point where this hyperplane is either as far or as close as possible to V. Okay. A is non-negative. The reason I say that is if I plug x equals x naught into here, what do I get? So if I plug x equals x naught into here, what's the value that pops out? What's that? Is it 0? So if I plug x naught into here, this goes to 0. This becomes u of x naught minus v of x naught, right? Which is positive, right? U is always above v. So I can make this positive, which means the maximum of it is certainly positive, right? So certainly a is greater than or equal to 0, since x equals x naught gives a non-negative value. Okay, so there's two possibilities. A is greater than 0 or A is equal to 0. So case 1, A is greater than 0. Okay, that means that A is equal to u of x naught plus p dot x1 minus x naught minus v of x1. This is a supporting hyperplane, right? For u. P is the gradient of u at x naught. So this is certainly less than or equal to u of x1. That's just the definition of the gradient or subgradient of a convex function. So this is since u is convex and p is equal to the gradient of u at x naught. And A, we said, was greater than 0. Okay, so that means u and v are not equal. True? Okay, u and v are not equal at this point. Is x1 in the interior or on the boundary? It's on the interior, right? U and v are equal at the boundary. So we can say x1 is not on the boundary. Okay, so let me write out all of this again. We have u of x naught plus p dot x1 minus x naught minus v of x1. This, by virtue of being a maximum, is certainly always greater than what I get if I put in any other value of x. Okay, and if I rearrange a little bit, v of x is greater than or equal to v of x1 plus p dot x minus x1 for all x. What does that look like? So where have we seen expressions like this before? V of x is greater than v at some reference point plus p dot x minus our reference point. What's that?
Maximizer.
It's a maximizer, but where do we see this kind of maximizer come up? All right, this is a definition of something. It comes up in the definition of the subgradient. Right? So in other words, P is in the subgradient of V at x1. Should be a P. And since x1 is an interior point, what do we know about the subgradient of V? We know that the subgradient of V is always contained in y bar. Right, you recognize this as the definition of the subgradient? Yeah, okay. You're staring at it like you haven't seen it before. So P is in the subgradient of V. The subgradient of V is contained in our target set. We checked that before. And what was P? P was the gradient of U. So that means that the gradient of U at x naught is indeed contained in our target set. That was the A positive case. There's also the A equal to 0 case. Okay. So again, I'm just going to write down what this is in general, right? Just like I did here. So this is for any x. We have that U of x naught plus P dot x minus x naught minus V of x, right, is always bounded by the maximum, right? And the maximum is now 0. So this is always less than or equal to 0. I can even write I'll write an in-between step in here. It's less than or equal to A, which is 0. So A is the maximum value, and the maximum value is now 0. Okay, again, I want to use something that I know about the subgradient of V, so I'm going to try to write this in a way where the subgradient of V somehow pops out. So let's write it as V of x is greater than or equal to U of x naught plus P dot x minus x naught. That's not quite the subgradient of V. What do I need to change in order to have something that looks like the subgradient of V there? I can use the fact that U is bigger than V, exactly. So wherever I am, U is always bigger than V. So if I make that one change here, now what do I have? Now again, I have something that looks like the definition of the subgradient. This holds for all x. P is my subgradient value, and now it's happening at the point x naught, not at the point x1. So here I can conclude that P belongs to the subgradient of V at x naught. And again, we know what the subgradient of V is allowed to do. It's forced to land inside our target set. So this is certainly contained in y bar. Right? So all that construction to say that if we force the simple boundary conditions, simple, they're nonlinear, right? But they're local. We have this nice sort of local nonlinear Neumann type boundary condition. If we just force that and look at the solution we get at the end of the day, it will also solve our original problem. At the end of the day, we can conclude that the gradient of U is contained in y bar for all points x naught. So a long construction, but with an outcome that's going to make life much easier in the future, because when we actually go to try to solve this problem, instead of saying I need to somehow do something globally with the whole gradient, I can now just say I just have some kind of normal looking boundary condition that I want to, say, discretize and hopefully use techniques, kind of normal numerical PDE techniques to solve the problem, right? And know that when I do, I'll get something that really does map everything into my target set like I want. Questions on that? So that's the Monge-Ampere equation. What I want to do next class is everything we've really done so far has talked about optimal transport with quadratic cost. I want to say just a little bit about how these ideas can generalize to some non-quadratic costs. A lot of the ideas are the same, it just everything gets messier. But we can also see some kind of nice elliptic PDEs pop out there. I'll leave you there today.